that idea. We'll just do math on the beach and do it in the sand.
Let's do it.
Yes.
All right.
Hey, Kirsty's running a hotel for all of us.
This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hey, I'm Lee Bortons, and it's Monday, March 6th, 2023. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss a math concept each week from our soon-to-be-released math curriculum for families with students enrolled in classical conversations communities. Kirsty, I love math because it helps me transfer my 3D experiences onto a flat surface called a piece of paper, which is not even 2D. Paper's 3D, no matter how thin it is. That's an exciting thing to think about. Kirsty, why do you like mathematics?
Well, I think maybe tonight I like mathematics because it lets me schedule my days. Today has been a really full day. I started the day in West Palm Beach, Florida, and ended up here. And I had to figure out, what route should we take? How much time did we have? And so math let me figure out that we could take the scenic drive down A1A instead of I-95. And it was much more enjoyable.
Oh, I love A1A. Okay, I also love Highway 12. For those of you that don't know, Highway 12 is the beach highway along the North Carolina coast where we live. You can actually drive your car up and down our state, right along the water's edge. All right, so this is week 9, which means we have 6 more book clubs. Did I get that right? Yes. Before we will be taking the summer off. That means summer's coming quick. The book club schedule is designed for parents who want to prepare to teach their children ahead of time. So now we're trying to get prepared for what's coming next fall. To access the Math Map, you need to be a member of Classical Conversations CC Connected Community. Please feel free to participate in the discussion, even if you're not in CC, as we will share the things you need to know on the screen. Each week, we consider a quotation or a image or a reflection that's part of the exordium for the Math Map lesson. Tonight, we're discussing the Math Map lesson 9, straight lines, and it's the first lesson in 2D geometry. Kirsty, what's tonight's exordium?
So tonight we are going to go ahead and just look at that beautiful piece of art. I think it's one of Lee's favorite pieces of art, and it is also mine, and it's become very meaningful to me because it represents obedience and the blessings that come from obedience. And so I won't go too deeply into that, but it has become very, very meaningful. But let's take a minute and see if anybody has any ideas why we chose this piece of art. Does anybody want to chime in?
Do you see any straight lines?
His legs.
They're lovely and straight, aren't they? Does anybody notice something along the back of the painting? You almost don't notice it.
The horizon.
Yeah, we talked about that in 1D, didn't we? That we can't really have a horizon that we think of, that's really an idea that we can't talk about until 2D, that idea of horizontal and where that horizon would be.
You can even see striations in the rock.
The lines. Good. Yeah, I like it because it actually always reminds me of what's coming attractions are too, because there's not just straight lines, but we have angled lines and curved lines, and we'll be devoting a week to each of those kind of lines. So 3 weeks of lines. So a lot of folks ask me how we do review in the Math Map, and that would just be an example that we keep talking more and more about lines.
And it's pink,
which I wear every time I'm on the book club. Where's your pink hair, Kirsty?
it's there. It's faded a little bit. It needs to be re-energized.
Well, if anybody has any comments about our flamingo,
Are-
feel
are
free.
there-
You wish. Good.
Are there light sketches at the top? Like, is that feet, or I don't know what that, like those light gray, are they sketches? Yeah, those, uh-huh.
So this is an Audubon piece, right?
It
Is it?
is.
Okay, that's nice to see.
So he does that in a lot of his pictures. He's got other parts hanging around as he was practicing. Which just goes to show that our kids and us, we can be artists, and it doesn't have to be perfect, and we can still become very famous and help folks see things well, even if you don't erase the extra feet in the air.
Lee, I think it's also a great reminder too that he didn't necessarily create art. I mean, he did create art, but that wasn't his purpose, that he was trying to do a study of birds, that this was really a science, more of a science project, right? It was a scientific diagram. And yet we look at it and we see the beauty in it. And so just that reminder that we live in this world that is trying to break things apart, and divide things out and separate things. But we know as classicalists, right, that everything is integrated. And so this picture that we're using to help us introduce the idea of straight lines, and we can also see curved lines and angled lines and all kinds of things going on in the painting, right? We're talking about it as a work of art, but it's also science, right? And then if we talk about Audubon himself, we can get into the realm of history and all kinds of things, right? There's so many things that we can talk about when we think about Audubon and the work that he has done.
That's right. Yeah, so those of you who have children that are artists and enjoy replicating what they see in the world, remind them they're also mathematicians. You have to help build their confidence. Okay, so we always talk about there's two things we're trying to identify through the math map. One, that since math is a foreign, though universal language, we have a lot of definitions that are assumed, and that's what can be confusing to students. And geometry, even though it's strongly a visual subject, it also does have language. And so you need to not give up on the grammar of geometry grammar while we're actually drawing beautiful pictures. And then the other one is that most people would define math as orderly, yet they aren't really able to identify a stable canon. I've been using the analogy that each small section of the math map has an underlying structure, kind of like latitude and longitude in geometry. And now here we are. We're going to be talking about geometry for the next, well, really for the end of our spring preparation. So feel free to turn on your camera and chat questions and comments at the bottom of the screen while Julie selects some for our discussion, and also get out your paper and pencil while we talk tonight about Math Map Lesson 9, Straight Lines. Let's see if we can learn any of the notations that go along with straight lines. Kirsty, what do you have for us?
Oh, so there's so much. I think that it's one of the things I love about what we do when we talk about 2D and geometry. We're talking about geometric shapes, but we're also talking about algebraic concepts. So we're not necessarily expecting our younger students to manipulate things algebraically, but we're going to introduce them to the ideas that these geometric shapes have equations that can represent them, that there can be measurements and formulas, right? That there's these geometry, the shapes and how we describe that, but there's also this idea of algebra giving us equations. And then there's also this idea of still the arithmetic, right? As we measure things and we assign numbers to things, right? That we have to understand the arithmetic. And these three pieces to come together. And I think geometry is one of the places where, or 2D is one of the places where we can really see all three pieces of mathematics really integrated. And so in the math map, we haven't separated those out like you may have experienced growing up, but we're really trying to look at them in an integrated whole of how we can look at these things from all of these different perspectives. So tonight with straight lines, we're going to talk about lines as a geometric shape, but we're also going to talk about lines and how we could define them algebraically, and what that looks like now that we can talk about more than just one number line.
That's great. I guess I want to point out too that, there's various forms of geometry. So when you were talking about the integration of it, just to help maybe familiarize some of you, if you ever took in high school a course called analytical geometry, that's where you were applying the algebra to the shapes. If you were doing something that's more along the lines of like Euclidean geometry, you were looking at the propositions, the constructions, and the proofs, which we'll be coming up on. But there's so much you can do with geometry, because it's really us replicating the real world, 3-dimension on 2-dimension, and it gives us a way to talk about it. Before the internet, I could mail you a letter that had geometry in it. Did we lose Kirsty?
No, I'm still here.
Oh, you look like part of the back. Okay, so I'm
Sorry.
done being smarmy.
So let's go ahead and look at our next slide and look at a specific idea. So as Lee pointed out, this week 9 is our first week in 2 dimensions. So before we jump into talking just about the straight lines, let's take a minute and talk about 2D and what does that mean. And the first thing that we want to encourage students and their families that are using the math map to do is to really recognize these patterns that start to emerge when we look at things by dimension. And so the answers to this are all over here. They're pulled from the chart. So this would be the first chart for week 9. And I've blown up that top left corner that sort of defines the second dimension. And so let's fill in this chart, pulling those answers. So how many dimensions are there in 2D? 2, where I see Donna holding up 2, right? So I know it seems kind of obvious. Let me find my annotation here. There we go. So we've got 2. So now let's go over here and look. So it says it can be represented by how many variables? 2. So we've got 2 variables. And then it gives us a shape. And what kind of a shape would you describe that as?
The way it's drawn, I would call it a cross, but it could also be an X if it was turned slightly.
So we'll go ahead and just for the sake of right, it does look like a cross, and then underneath that, what does it name that as? What's this word here?
A plane.
A plane. So we would have a point, and we would have had a line, and then we've got our coordinate axes is our picture that we're using, but we're going to call our shape a plane. And then let's look at what it says about size. So going back to 0D, we said there was no size, there was no height, no breadth, no width. Then in 1D, we said we now have infinite length. What do we have in the second dimension? How does it describe it?
Would it be infinite area?
So let's think about size. If I want to talk about 2 dimensions, what 2 dimensions, how would I measure something? So if you were going to measure a piece of paper, you would talk about its length and its width. So that idea of infinite is right? So we see that here, this infinite length and width. So let's go ahead and put that there, infinite length and infinite width. And then that long measure, that's where, I'm not sure who it was that said it, right? But you're right. That's where we're going to talk about area. So now that I have 2 dimensions, I can talk about area. Now, we may not be able to fill in all of these things, but looking at the patterns that we have there, all right, 0D was 0 dimensions, 1D was 1 dimension, 2D was 2 dimensions, How about 3D? How many dimensions do you think?
3.
3. And 4D?
4.
Or
4. Okay. So notice here, we haven't talked about 3D or 4D. You don't know anything about that yet from our calls, but already you know that when you hear 3D, you're talking about 3 dimensions, 4D, 4 dimensions. So let's look at variables. It looks like a similar pattern. 0 variables in 0 variables in 0D, 1 variable in 1D, 2 variables in 2D. How many variables do you think you'd have in 3D?
3.
3. And how about in 4D?
4.
4, right? Now, here's where it gets a little bit harder, right? Because we haven't talked about these names. And so where you go point, line, plane, anybody have any ideas of what we might call 3D?
Would it be something like a cube or a polyhedra? Or
So you're
polyhedron,
right.
sorry.
So those are 3-dimensional shapes. And when we get to 3D, we'll talk about one of the limitations of thinking about it as a cube. But it has to exist in our space, right? So we call it human space. So some places might just call it space, and we tack on, I'm going to write it sideways just because it won't fit. And we tack on human space just because we really want to emphasize it's where we live. And then I think that 4D, what we call 4D, is really fun because we call that hyperspace. So if anybody's a Star Wars fan, right, we're going to go look at hyperspace. We can also call it intersected space, right? So there's different names that we might come up with as we get to these other dimensions. There's a little bit more wiggle room for some of the names. But when we talk about size, let's go back and think about a point, and a point had no height, no width, no depth. And then we said that 1D had infinite length, 2D had infinite length and width. So 3D we think is going to have infinite length, infinite width, and infinite depth. Right?
Yep.
So I'm
We have height in here on your chart, Kirsty.
height.
Yeah.
So height, depth, right? So sometimes we might use different words, but it's that same idea. And then in 4D, we're going to use a word called breadth, which is a biblical word that gives us that idea of that 4th dimension, right? So obviously it would have all of these. I'm just going to add the ones that we would add in. Now you might know 3D, we've had length, then we have area, right? The surface. Anybody have any ideas of what we would call 3D?
Volume.
Volume. And then we're going to use capacity in 4D. So
Kirsty, do you mean to have breadth there in the under size for 4D instead of depth? Should that be?
Yeah, I
breadth?
did.
Okay.
Sorry.
The thing is, there's a Bible verse that tells the 4 dimensions, and depending on the translation, it substitutes these words, but they all have height, length, and width. And then sometimes it's depth and sometimes it's breadth, depending on the translation. But the idea that it's just to me amazing that scripture talks about 4 different, like none of those will ever separate you from the Lord. It's pretty amazing.
Do you know what verse it is? Renato?
No,
Romans
not off the
8.
top of my head. Let me know what it is. Here,
Romans
I'll look
8.
it up while Kirsty talks.
So I
Romans
just
8.
wanted to fill that chart in with you because that's an example of something that our students and their families are going to do every time they hit a new dimension, right? So they're going to continue to fill this chart out and can continue to add to it and continue to add to it year after year. And there's a lot more things that we could talk about in here, right? I just wanted to pull some things that were right there off of the chart, right? So that we could pull those things out. And then I filled in some of them because we went ahead, right? So our students would normally be building. But I wanted you to see that a lot of these patterns, we can start saying ahead, well, what would that next thing be? All right. And that's one of the powers of mathematics, is the idea that we can look at patterns, and using those patterns, right, we can look at what we know, what we can experience, what we can see, and we can predict, right, what is unseen, right? That we can start to get a glimpse of what might be out there in the unseen, of what the things are, right, that we might have to take on faith. So
let me add a couple things if you don't mind, Kirsty. So point, line, and plane. A plane can actually get stretched to a cube, and a cube can get stretched in 4 dimensions to something that's called a tesseract. And a tesseract, some of you may recognize from Madeline Lengel's book, she used that. The kids would use a tesseract to go from one dimension to another.
So yeah, so there's a lot more we're going to talk about in 3D and 4D, where we're going to stretch our minds. But we're going to stretch our minds by picturing what would happen if the pattern continues. Right. And so that's why every time in the math map, every time we hit a new dimension, we're just going to hammer this pattern, right? What do you think? What happens now? What's the new thing that we can add to our chart? So
Can I ask a question about 4D real quick?
Mhm.
So I remember working with 3D equations and graphing in 3D space and whatnot. I go back. So we were graphing in 2D at the time. But then we converted into parametric, and everything all of a sudden was in terms of time. The X equation, a Y equation, where time was an independent variable. And it just by converting into parametric, it kind of introduced a new dimension, and we would graph on the calculator, and like their jaws dropped by seeing a little ball travel across the calculator, like, oh, it can do it in time. And I feel like I'm geeking out, but I'm curious, like, you can have very easily 3D parametric equations that are all based off of a 4th variable of time. So I was always kind of wondering, like, us in our world that we have today, like, yes, we live in 3D space, but we also live dependent upon time. So where does time, what's the right word? What's the proper place of time when we think of dimension? I think is my question.
So I'm going to give you my answer, and then Lee may have some things to add. I like to think, so there's a place in the math map where we talk about time most specifically, and we look at it when we do talk about 4D. We use it there to help people picture, I can have a 3-dimensional location that's now moving in time. And so it gives us a way of picturing what 4D-ness might look like, although true 4D-ness we can't really see, but it gives us something to think about. It gives us something that we can picture. But I like to think of time as this bridge between dimensions, because I can have one point, right? So here's my little point,
been developed.
and then if that point moves, right, in order to describe that motion, right, I need in time, I now need another dimension, right? So that bridge, that time that allows that point to move is this bridge from 0D to 1D. And now if I have a line, and then in some period of time that line moves, in order to describe that motion, I need another dimension, which would be the plane, right? And now if I have, picture these as planes, if I have a plane and that plane moves in time, right? It has another location. In order to describe that movement, I need another dimension, which would be space, that 3D-ness. And now picture, if you would, and this is what I was alluding to earlier, and this is why it's so hard, because we think, okay, that's 3D. And if it moves, right, so we think, oh, there it is, and it's moved, and I can kind of see it still in 3D-ness. When we really talk about 4D, I'm talking about an entire space. So this is representing something that is infinite. And I think it's easier for us to picture an infinite line or an infinite plane than it is for us to think of an infinite space. because it feels so concrete. And so to picture this as like bigger than our universe because it's infinite, if that was to move in time, now I need the fourth dimension to be able to describe that movement of that space, and then so forth. So while time, we can think of time as being a variable, I think it also is a bridge from dimension to dimension. And when we talk about parametric equations, and we're way far ahead of where we really need to be, so I should probably stop talking. Parametric equations, that parameter oftentimes is not really a variable necessarily. It's a counter, right? So really, if I'm talking about 3D space, I'm really talking about three coordinates that depend on a counter, right? That as this fourth thing changes, where do these three things go? So it's a little bit different. I think colloquially might say, oh, well, it's a fourth variable, but it's not necessarily, it's a parameter. It's a little bit different, but we'll talk
would
about
you
that.
say, to kind of reiterate, make sure I'm understanding you properly, would you say that time is like transcendent of dimension?
I think it kind of to some degree operates outside. So time is the only measurement that I've discovered, right, that God really gives us. I mean, there's other measurements that are described in the Bible, but time is the only one that God really says, and this is what the measure is, right? That I've given you the day, right? And the day is measured by the sun, and I've given you seasons, and I've given you these ways of measuring time. So to me, everything else sort of like rests on that to some degree. I mean, even when we think about the standard units that we talk about, you know, they're like a second is how far this, like, right. When we talk about what things are, we're talking like meters. It's how far something goes in so many seconds. And so everything kind of comes back down to this idea of time. So it is, we certainly can use time as a dimension. We certainly can use time as a variable, but I also think it's something that's bigger sort of than that.
The only thing I would add is, good question, Beth. For those of you that don't know what she just asked, you will if you go through the math map, because we actually do parametric equations as well as matrices. And the thing that I love about them is not only are they consistent in all dimensions, but they allow me to do n-dimensional math without a lot of struggle. Versus if I don't use parametric equations or matrices, I can pretty much do two-dimensional math and some three-dimensional problems, but not very many of them. I mean, they're just too hard for me. So in a kindergarten through 12th grade kind of curriculum, we've chosen to use time as the fourth dimension, just so students will get the feel that there can be other factors. Kirsten, I think you brought before, like, is color a dimension? Like, it's a good question to ask. What are other dimensions besides these long measure ones? And how do they fit into our 3D world? So it's map is very mysterious, but it's also very calculable and understandable to a certain level. So good question, Beth. There's a bunch of stuff in the chat. Do we need to go over these?
I just wanted to, I noticed, Donna, when we talk about the plane, and I think maybe you guys have answered this within yourselves, but when you talk about the plane, we're going to use this image right here to talk about 2D. But yes, when we get into 3D, we're kind of trying to show, we do use a parallelogram-ish figure to represent planes, just to try and help us see how a plane, right? We're just showing a portion of a plane that's really infinite. If we try to use that 2D cross, right, within a 3D picture, that would really get confusing. So that's really what we're trying to do, is just represent that So let me know if that doesn't clarify that, but it seems like you guys are having a good conversation about that maybe answered those questions.
I think I understand why there's a difference, but why don't you use the parallelogram in addition to or beside this one or in this? Because just for that consistency, I know y'all talked about consistency before with other things.
Well, because I think here because really in 2D, right, we're trying to say here's the coordinate system for 2D, right? So this is the rectangular coordinate axis, and we're going to see that we also have the polar coordinate axis, and we're going to talk about complex numbers, which are rectangular, right? But then, so what we're doing here is we're not just representing a plane, but we're representing the whole coordinate system in 2D versus when we get to 3D, and I'm just talking about a plane, right? I'm just talking about now, just like here, I'm going to see I can have multiple lines in that coordinate system. In that 3D coordinate system, I can have multiple planes. And so that's where I'm still going to see that I have, right, in 3D, we're going to see that I've got, let me talk. We're going to have, right, we're still going to see that rectangular system for the axes, but then we want to be able to represent a plane within that. And so that's why the shape is different, right? It's just
The other thing
use
is,
of it.
go back to the math map slide. That's a couple back. Maybe we haven't pointed this out well enough. Do you see? So if you, with the one before where 3D showed up too. No, keep going, one more. There we go. All these are is mnemonics to trigger the student. This is a positive trigger. To trigger the students to go, that's right, 2D means I can go left and right and up and down. And 3D means that's right, I can go left and right, up and down, and in and out. It's just a mnemonic at this place. It's not how it affects the lessons. But if you have good ideas about this, Donna, send us a page. I'd love to look at it.
No, I like it's the answer. I think I heard that satisfied me was that it's the coordinate axis
That's all
versus
it is.
more of a representation. So yeah.
Yeah.
So has Disney done it right, creating the 4D theater for Lilo and Stitch, where we can actually we can get spit on?
Yeah, use that, Julie.
Yeah.
Good.
Uh-huh.
You got 3 dimensions in time and 3 dimensions in spit.
Yeah. The Shrek one is even worse. I don't know if you've been in that, but
Yeah.
there's sense of
Muppets blows bubbles.
yeah.
The thing is, I mean, what a good question to ask your kids. Pay attention to your space. And then when you're on like one of the best Disney rides I ever went on was that one where you hang and you're like there's a big screen in front of you and all your senses are confused and you think it's called soar. You think you're soaring. And I thought, okay, so a screen could really make it so that I think I'm in spaces that I'm not even in. Right. So wherever you go, always be looking for math concepts to talk to your kids about.
All right,
Oh,
we'll
is
do
it
the
time for
ad.
my ad?
It's time for the ad.
Oh, I gotta pull it up. Okay. I like to thank our sponsor, ccconnected.com, where the math booklet discussed by the club can be downloaded by Classical Conversations members. Look ahead to the book club schedule on leebortons.com under the Math Map Book Club tile, and it'll suggest that you work through lesson 10, intersected lines, before next week. So go to CC Connected to download the Math Map Naturals, which is in beta form, which basically means it's still being fixed. All right, so thanks for showing up. Okay, so what do we have next, Kirsty?
So for sort of thinking through talking about lines, I've got more to erase here. It's interesting to me that this persists. Okay. So when we talk about lines in 1D, how many lines did we have? We just had one, right? And you're going to see that we try to emphasize for students in the math map that we can talk about a line that's oriented this way on the page, right? And we can't really talk about how it's oriented in general because that's the only one that it is. But we do a lot of measurements with that line. And we use it as a coordinate axis. So we talk about things like X or less than or greater than or hops, right? So we talked a lot about that when we were talking about arithmetic. Then we also do a lot of work with lines that are oriented like this by themselves. And so things like thermometers, right? If you think about a thermometer, usually we measure that in this orientation. Is there anything else you can think of that we oftentimes measure in this orientation by itself?
Think of floors, like stories of a building.
Okay. So if you were just taught, right? So there's different things we can think of as just going this way. And so then the key idea, right, is, I'm just going to get rid of that extra, is that now we have two lines. And so to find where I am, right, when we were doing, just going to see here if I can do, nope. Sometimes I can do like a thing, but we're just gonna, right, if I was to talk in 1D, right, I might say, okay, my position is at 3. But if I say my position is at 3, does that tell me exactly where I am in 2D? No. If I just have one
Be anywhere
coordinate,
on that line.
it could be anywhere on this line, couldn't it? Right? If I say that X equals 3, it's anywhere on that line. Right? So how many coordinates do I need to know where I am in 2D? 2, right? And so I need to also know, let's say that this is 2, that Y equals 2. And guess what? Where they intersect, that's my point. And I live at 3, 2. Right? And this is very much like our latitude and longitude, right? You have two lines, and where they intersect, that's where your position is. Well, so notice that how many lines do I currently have drawn through that one point?
It's like Jesus. If you're in 2 dimensions, 2 is always the answer.
I have 2, but now how many lines could I have going through that point?
Infinite number.
Infinite.
I could have an infinite number, right? So let's just draw some of them, right? I might have one that's here. I might have one that's almost vertical. I might have one that's almost flat, right? And so I just keep going around, right? And so I could keep going around, and just like points on a number line, right? I could keep drawing those lines in, and I could have an infinite number of lines through that point. So is one point enough to tell me what line I'm talking about?
No.
No. It tells you the point.
It tells me one point on my line. So what else could tell me which line I'm talking about?
Any other point that's on that line?
Well,
Any other point? So how many points would I need to define one line?
Just 2.
Just 2, right? And so
2.
if I said, okay, I want it to go through, let's say that this is 4 1/2. Now you know that I can erase all of those other lines, right? Make sure I don't erase the wrong one, right? I can erase all these other lines. Oops, I didn't really mean to erase those. I appreciate everybody being patient with me and technology. And now I know that is the only possible line that goes through those 2 points. Right. So now let's look at that picture that's on the left-hand side, right? And notice that there's 2 points that we have listed on that line, and we call them some different things, right? We have a point that's XY that represents some point that's on the line. We have another one that's named the intercept. Now, what does intercept mean?
Just the
Anybody
place
know?
where the line crosses the y-axis.
So in this case, we're talking specifically about the y-intercept and where it crosses the y-axis. But if we just think in general, right? If you've got boys in your family and they like football, right? What's an interception, right? It's where
Somebody stole the ball.
somebody on the other team, right, got in the way and they caught the ball, right? They intercepted, right? And they said, no, we're going to cross it right here. And so that's that same idea of intercept, right? It's where the y-axis is catching the line. Is really what that's saying, right? Does that have to be the point? So look at our example.
No.
No, it doesn't. It's a convenient point because the y-axis is where x equals, anybody know? 0. And I love the fact that Lee will sit there and say that 0 is her favorite number because it usually means the problem is going to be easy, right? It's going to be an easier calculation. And so no matter how ugly right, I could have like 4.37 divided by 96 all raised to the like 42nd power. I don't know, I'm trying to like come up with really ugly things. And then if I just say times 0, right, all that ugliness goes away. And so that's really why we like the y-intercept, because I can stick a 0 in the place of x, and it makes things a lot easier to simplify arithmetically. So we've talked about the fact that 1 point wasn't enough. As soon as I have 2 points, it's going to anchor it. And I just want to talk about one other thing is over here, just let me find my line again, right? Does this sound familiar to anybody? Slope?
Yep.
Just in general, so don't think mathematically, right? When you hear the word slope, what do you think of?
Rise over run.
Okay, so that's a mathematical answer.
A roof.
A roof,
A roof.
You know, skiing.
skiing,
Ski slope.
Mm-hmm.
Slant.
a slant, right? So a lot of times when we think of something that's slope, we think of things that are not flat.
Incline.
And an incline, good,
Like a truck sign that says what the incline is.
good. Globally, a lot of people don't use the word slope. They actually use the word gradient to describe, because I think a lot of times that when we think of trucks and hills, we think of gradients, right? Interestingly, when I think about things mathematically, I always think, oh, 45 degrees isn't really that steep. And then you start to think about what is considered steep in the real world, and you realize that like none of us could drive up a 45-degree incline. So that word slope is just describing the incline, right? How steep it is compared to being flat, right? So if it was flat, there's no change. We say our slope is 0, right? Other than that, we're always going to be moving. So here's some ideas, right? We're always moving left to right. So we're always going to be talking about how does my line change, my y value change as I move from left to right. If it goes up, what kind of numbers do you think we're going to use?
Positive.
Positive. And if it goes down, we're going to use
Negative.
negative, right? So let's look, and I'm just going to suddenly say, let's say I told you what the slope of the line was instead of the point. Right, so let's go back to, right, we only have 1 point now. But if I had said to you, it's the line that has this specific slope, right? And let's say that we were, is it positive or negative? Are we going up or down as we go left or right?
Down.
Down.
Down. So we're going to go negative, and let's just say it's -2. I'm going to make something up, right? Well, there's only one line that has a slope of -2. But what if that's all you knew? How many lines have a slope of -2?
Infinite number.
Infinity.
An infinite number, right? So, and what do we call these lines? This is really next week's lesson, right?
Wow.
Parallel.
Parallel, right? So let's go back, and if I didn't know this point, and all I knew was the slope was -2, what would I need to tell you in order for you to know which line that I was talking about?
Any
Excellent.
point on that line.
Some point on that line, right? It could be the intercept, right? Let's say I wanted this line, I might pick the intercept, but
But
I
I need a
could,
point on the line.
I can pick any point on that line, but as soon as I know one point, I know which line I'm talking about, right? So how many pieces of information do I need to know about a line?
2.
2,
Great.
right? I need to either know 2 points or 1 point and the slope, but that's still 2 pieces of information, right? So 2D, I need to know 2 pieces of information to know specifically which line I'm talking about, right? And so it's kind of mind-boggling, isn't it? Because how many lines are there in 2D?
Infinite.
Infinite.
Infinite, right? Like there's just this in like, and they overlap each other. Like there's so many lines that when you start thinking about it, like it's not even just like, oh, I can draw them all around this point, right? But every point has an infinite number of lines. So there's just like this infinity of lines in 2D. And isn't that amazing that
It
for
is.
1D there was one line, that was it. And as soon as we add another dimension, right, how many different lines there are? I don't know. I just, right, that to me is that gives you that sense of when God says, like, my ways are higher than your ways, right? And you can't begin to imagine just this alone, just talking about going into 2D and how many possible lines there are, right? But you only need 2 pieces of information to identify any one of them.
Perfect. That's the gospel. I mean, he had to come down, and then there was infinite. It's very beautiful.
Actually. All right, thank you once again, Kirsty. That was wonderful. Thank you, team, for being here and for practicing math with us. We look forward to seeing you next week when we're going to talk about intersected lines. What is the most interesting intersected line you can think of? Tell us next week. Bye.
Bye.